Uh, Welcome everyone. Today we will be looking at real numbers, and we will be looking to prove that real numbers are an ordered field. Now, in order to do so, we present two definitions. Definition 1. Suppose Z is an element of the real number field. We say Z is non-negative if for some representative Cauchy sequence Zn, where n is an element of natural numbers, for each n is an element of natural numbers, the tangent term Zn within the Cauchy sequence is greater than 0. Informally, we can say that we require the existence of a Cauchy sequence Zn, which is everywhere positive. Now, note that definition 1 calls for the sequence Zn to be everywhere positive, but only describes the corresponding term Z as being non-negative. Why is that so? This is because the convergent sequence of positive rational numbers may actually have a limit 0. In that sense, an everywhere positive Cauchy sequence can indeed converge to 0. An example of this is the sequence defined by an equals 1 over n. Now we know that that sequence an equals 1 over n would tend towards 0 as n tends towards infinity. And well, we don't exactly want to call 0 a positive number. That would lead to a lot of complications. This is why we say that for a Cauchy sequence that is all positive or everywhere positive, there exists a corresponding Z, which is a real number that is non-negative. Definition 2. We defined a relationship less than or equal to on R by the following. If x is less than or equal to y, then y minus x is non-negative. We can kind of use definition 1 to interpret this as x is less than or equal to y if there exists a Cauchy sequence that represents y minus x that is everywhere positive. Now, we call this relationship the order on R. So, having defined our terms, we now attempt to prove the proposition in hand, which is as follows. The relation less than or equal to is a total order on R. Now, how do we prove this? Well, by showing that the relation adheres to the 4 properties of a total order, which are as follows: reflexivity, antisymmetry, transitivity, and totality. We first attempt to prove reflexivity. Assume an x, which is an element of the real number field. We know that negative x would be the additive inverse of x, so negative x is equal to 0 minus x. This implies that x minus x is equal to 0. Now, we know that the Cauchy sequence, which from here on out we'll write as CS, the Cauchy sequence an equals 1 over n belongs to the equivalence class, which we now write EC 0R. Therefore, for every n, which is a natural number, an is larger than 0. So we know that an is a positive, an all positive Cauchy sequence, and we know it belongs to the equivalence class 0R. Therefore, this implies that x minus x is non-negative, as x minus x can be represented by an all positive Cauchy sequence, and thus x is indeed smaller than or equal to x. This makes sense. We then attempt to prove for antisymmetry. Suppose we have an x which is less than or equal to y. This implies that y minus x is non-negative. Similarly, now suppose we have a y which is less than or equal to x. This implies that x minus y is non-negative. So, given what we have supposed, we know there exists a positive Cauchy sequence, Zn, that represents y minus x. Similarly, we know that there exists another positive Cauchy sequence, Z prime n, that represents x minus y. This is because we suppose that both y minus x and x minus y are non-negatives, right? So we know that the additive inverse of the Cauchy sequence Zn is negative Zn, because Zn minus Zn is 0. Therefore, we know that the Cauchy sequence negative Zn represents negative y minus x, right? The additive inverse, which is x minus y. This tells us that there is indeed a relationship, an equivalence relationship at that, between negative Zn and Z prime n, both Cauchy sequences. This implies, and recall that when Cauchy sequences have an equivalence relationship, what this means is that one Cauchy sequence minus the other tend to 0 as n tends to infinity. So in this case, right, we suppose that z prime n minus negative zn tends to 0 as n tends to infinity, right? So simplifying this, we can say that z prime n minus zn is equal to z prime n plus zn. Now recall that we assume that z prime n and zn both represent non-negative real numbers, and thus they are both all positive. This means that we can take them out of the absolute value, as well they're all positive, and keeping them in doesn't make a difference. So we can say that z prime n plus zn is equal to absolute value of z prime n plus absolute value of zn. Now, seeing as the absolute value of z prime n plus zn tends to 0, well, and they're both all positive, by force, zn and z prime n both have to tend to 0, because they can't be negative, they're absolute values, and they tend to 0, so the only case this would be true is if it's 0 plus 0, right? So we know that zn and z prime n tend to 0, therefore we know that x minus y equals 0 and y minus x equals 0. Simplifying this, we know that x equals y. So we have thus proven that if y is less than or equal to x and x is less than or equal to y, forcibly x is equal to y, and that is proving antisymmetry. We now attempt to prove transitivity. Now, suppose that x is less than or equal to y and y is less than or equal to z. Then both y minus x and z minus y are non-negative. So there is an everywhere positive rational sequence, right, which will denote alpha n and beta n, that represents the equivalence class y minus x and z minus y. Now, we know that z minus x is equal to z minus y plus y minus x. And seeing as we know that z minus y is in the same equivalence class as the Cauchy sequence beta n, and y minus x in the same Cauchy sequence equivalence class as alpha n, we can denote z minus x as being in the same equivalence class as beta n, the Cauchy sequence, sorry, of beta n plus alpha n. We know that beta n and alpha n are both everywhere positive, as we assume y minus x and z minus y are non-negative. So we know that the addition of two everywhere positive Cauchy sequences is also everywhere positive, as proven in proof so far. So we know that z minus x can indeed be represented by an all or everywhere positive Cauchy sequence, alpha n plus beta n. This therefore implies that z minus x is non-negative, which implies that z minus x, is non-negative, which therefore implies that x is less than or equal to z. We have thus proven that if x is less than or equal to y, y is less than or equal to z, x is less than or equal to z, proving transitivity. We now prove the last of the four, totality. But what exactly are we trying to prove with totality, right? What we want to prove is that for every x, y, which is an element of the real number field, if x is less than or equal to y is false, then forcibly y is less than or equal to x. How do we prove this? Suppose that for x, y, which are both elements of the real number field, x is less than or equal to y is false. This implies that y minus x is not non-negative, and it also implies that the Cauchy sequence representative of y minus x, zn, is not all positive. But how many non-positive terms should zn have? We'll explore that. Now suppose we have a Cauchy sequence alpha n that is all positive. Suppose that every term in the sequence is positive. Oops, this is also, this is not, the sequence doesn't end at alpha 7, by the way, just they all, Cauchy sequences are infinite. Oh, yeah, that's important to note. So suppose we have a Cauchy sequence alpha n, which is all positive. We thus know that it tends to a non-negative number, real number a, right? Now suppose we have kind of a subsequence of alpha n, which we will denote alpha Rn, where we take out finitely many terms from the original Cauchy sequence alpha n. Now we know that this also tends to the same non-negative real number a, as proven in proof so far. Now suppose where we have this sequence here, alpha prime n, where we kind of fill in the blanks left by alpha Rn with finitely many negative terms. So here, instead of alpha 1, we'll put negative 1. Instead of alpha 3, we'll put in negative 5, alpha 5, negative 10. It doesn't matter as long as there is a finite number of negative numbers. we know that there's a relationship between alpha prime n and alpha Rn because alpha Rn also kind of acts as a sub-Cauchy sequence of alpha prime n. So we know that alpha prime n has to tend to the same number as alpha Rn. And we know that alpha Rn tends to a non-negative non-negative real number a. Therefore, alpha prime n has to tend to a non-negative real number a as well. We have thus proven that alpha n has an equivalence relation with alpha Rn, which has an equivalence relation with alpha prime n, in turn proving that a Cauchy sequence with a finite number of non-positive terms will tend to a non-negative number, right? As a result, if we want a Cauchy sequence that tends to a not non-negative term, we need a Cauchy sequence that has infinitely many non-positive terms. Right, so here, finite does not work. So we can kind of explain this a little more formally, right? Suppose we change, take out, or add finitely many negative terms to a Cauchy sequence, or finitely many terms in general, right? Recall the definition of a Cauchy sequence. For every epsilon that is greater than 0, there exists an n such that for every small n and small m, bigger than big N, xn minus xm is smaller than epsilon, right? So what we do here is this. If we change or add or remove a finite number of terms to a Cauchy sequence, we have our fixed epsilon, which is bigger than 0, right? And just according to how much we change the Cauchy sequence finitely, we can just shift our arbitrary n accordingly. If we say add 10 negative terms to the Cauchy sequence in the start, we can just shift down our n 10 terms, such that instead of, because n is arbitrary, right? So we can just kind of adhere it to the Cauchy sequence that we create. And that is why if we change, add, or subtract finitely many terms within a Cauchy sequence, the Cauchy sequence still tends toward the same number, and it's still bounded by the same epsilon, right? This is why for y minus x to be not non-negative, it needs a representative Cauchy sequence Zn that has infinitely many non-positive terms, right? So we suppose again that Zn is part of the equivalence class y minus x, as we have before. We then suppose that we take a z prime n, which is equal to the additive inverse of Zn, which is negative Zn, right? So this tells us that z prime n is in the equivalence class negative y minus x, which makes it in the equivalence class x minus y. Now, at this point, it is important to note that just because Zn had infinitely many non-positive terms, this does not imply that every term in Zn was non-positive. Similarly, Z prime n has infinitely many non-negative terms, but this does not imply that every term in Z prime n is non-negative. Now, in order to get around this, we present a Cauchy sequence Z prime Rn, which we define as being all of the non-negative terms of Z prime n, right? We know from proof so far that Z prime Rn would be a Cauchy sequence. And we know that Z prime Rn has an equivalence relation with Z prime n. Also, we know that for every n in the Cauchy sequence Z prime Rn, Z prime Rn is greater than or equal to 0, because every term Z prime Rn is non-negative. However, just because every term is non-negative, this does not imply that every term is positive, right? So for that, we take the Cauchy sequence of So now suppose the Cauchy sequence Z prime Rn plus 1 over n. Now we know this Cauchy sequence is greater than or equal to 0 plus 1 over n, which is greater than 0. This is because the Cauchy sequence defined by 1 over n is all positive, as we suggested before. Every term in the Cauchy sequence an equals 1 over n is indeed all positive. We also know that this Cauchy sequence, right, tends to 0 as n tends to infinity. This is all to imply that the Cauchy sequence Z prime Rn plus 1 over n, which we know to be all positive, is greater than, has an equivalence relation, my bad, with z prime Rn, which also has an equivalence relation with z prime n, right? All of this is to say that z prime n, recall that z prime n is the Cauchy equivalence class of x minus y. So we know that x minus y, which can be represented by z prime n, has an equivalence relation with z prime Rn plus 1 over n, which is all positive. This implies that x minus y is indeed non-negative. So we know that if y minus x is not non-negative, x minus y is non-negative, as we have proven by its Cauchy sequence being all positive. Or its Cauchy sequence having an equivalence relation with a Cauchy sequence that is all positive. So yeah, this all comes to imply that if x is smaller than or equal to y is false, y is smaller than or equal to x. And thus, we have proven totality, and we complete our proof. Thank you. I realized I forgot to add tombstone, so tombstone, very cool. And we have thus proven that the relation less than or equal to is a total order on the real number field.